4. So by simplifying all this, I will get here, this is 6, 4 plus 1 plus 1, 6, minus 2 minus 2 minus 1, that is minus 5. Here 2 plus 2 plus 1, that is 5. Here minus 2 minus 2 minus 1, that is minus 5. Here 6, here minus 5, here again that is 5, again this is minus 5, and this is 6. So if we look at the PPT here, then here we have write that the a value of a square, that is a into a, will be 6 minus 5, 5 minus 5, 6 minus 5, and 5 minus 5, 6. So in this way we can find the value of a square. In the same way, by multiplying a square with a, we will get the value of a cube, that will be 22 minus 22 minus 21. Second row will be minus 21, 22 minus 21. Third row will be 21 minus 21, 22. So the calculation of finding a cube will be in homework for the students. We have already discussed how to multiply the matrices a into a. So now students need to multiply a square with a, and the result is yours, that is a cube. If we look at the PPT here, we have the value of a square, we have the value of a cube, and now if we substitute all these values in the left hand side of the equation number 1, that is a cube minus 6a square plus 9a minus 4i. So we will get here, this is the value, right? So this is the a cube minus 6a square plus 9 into a minus 4i. And if we do the simplification of the left hand side, we can easily check that here the value will be 0 0 0 0 0 0 0 0 0. That is the null matrix, which is the right hand side of the equation number 1. So here we have proved that this equation, this matrix A, satisfies the characteristic equation of it, right? So that means this matrix satisfies the characteristic equation. That means we have verified the Cayley-Hamilton theorem, which is the statement of the Cayley-Hamilton theorem, that is every square matrix satisfies its own characteristic equation. So here we have proved that, we have verified that the matrix A satisfies the Cayley-Hamilton theorem. Okay, well, satisfies its characteristic equation. So now using this one, we also need to find the value of A inverse. Now we have a cube minus 6a square plus 9a minus 4i is equal to 0. And now if we pre-multiplying both sides by of equation number 1 by A inverse, we will get a square minus 6a plus 9i minus 4a inverse is equal to 0. So now simplifying that, we will get 4a inverse is equal to a square minus 6a plus 9i. We have already a square which we have find here, that is 6 minus 5 5 minus 5 6 minus 5 5 minus 5 6, that is a square, minus 6a we have already a, and 9 into I, where is I is the identity matrix of 3 cross 3, is equal to by simplifying this expression we will get 4a inverse is equal to 3 1 minus 1 1 3 1 minus 1 1 3. So the A inverse is equal to 1 by 4 into the matrix 3 1 minus 1 1 3 1 minus 1 1 3. So here we have find the value of A inverse. So in this way, using the Cayley-Hamilton theorem, we can find the value of A inverse for any matrix which is given. Okay, so now also I want to say that we all know that we can also find A inverse using adjoint of A upon determinant of A. So we can also find the A inverse using that formula, adjoint of A upon determinant of A. Here we have find the value of A inverse, that is equal to 1 by 4 into multiplication 3, 1 minus 1 1 3 1 and minus 1 1 3. So student can verify this result of A inverse. They can find easily A inverse using adjoint of A and determinant of A. And student, this is the homework for the student to check the result of finding A inverse using that formula, adjoint of A upon determinant of A, and you need to check that the result of A inverse by that method must be equal to this result. So this is the homework for the students. Note down the value of A inverse by this result, that is 1 by 4 into the matrix given in the PPT. So note down this result, and you need to find the value of A inverse using adjoint of A upon determinant of A. So this is the homework for the students. Now let us move. So one more example. The question is, given A is equal to 1 2 minus 1 0 1 minus 1 3 minus 1 1, find adjoint of A by using Kelly-Hamilton theorem. Right here, the characteristic equation of the given matrix, that is A minus lambda I determinant is equal to 0. So the determinant of 1 minus lambda, 2 minus 1, 0 1 minus lambda, minus 1, 3 minus 1, 1 minus lambda, that is equal to 0. And by expanding the determinant, we will get the equation will be lambda cube minus 3 lambda square plus 5 lambda plus 3. In the last example, we haven't repeat that how to expand the determinant. Here I want to repeat how to expand the determinant. So the students who have not idea that how to expand the determinant, please look at here. We want to expand here 1 minus lambda, 2 minus 1, 0 1 minus lambda, minus 1, 3 minus 1, 1 minus lambda. Okay, that is equal to 0. We know that to expand this one, we will multiply with all the elements of first row with its cofactor. So here 1 minus lambda into, that is 1 minus lambda into 1 minus lambda, that is 1 minus lambda whole square, minus this one into this one will be 1 minus 2 into 0 into this one, that is 0, minus 3 into minus 1, that is minus 3, so this is minus minus plus 3, and minus 1 into 0 into minus 1, that is 0, minus 3 into 1 minus lambda is equal to 0. And now all students know that how to simplify this one. Okay, so by simplifying this one can get the equation as I have told you in the PPT, that this one is equals to lambda cube minus 3 lambda square plus 5 lambda plus 3 is equal to 0. I also explained how to give the simplification of this one. Okay, so this is the characteristic equation for the given matrix. Okay, so by Kelly-Hamilton theorem, the matrix A should satisfy its characteristic equation. Then we will get a cube minus 3a square plus 5a plus 3i is equal to 0. And by pre-multiplying by A inverse, we will get a square minus 3a plus 5i plus 3a inverse, that is equal to 0. So by simplifying, we will get A inverse is equal to minus 1 by 3 into a square minus 3a plus 5i. That is our result. Now we need to find the value of a square because we have given a. So by multiplying a with a, now every students know that how to multiply the matrices. So a into a, so we need to multiply 1 2 minus 1 0 1 minus 1 3 minus 1 1 with itself. Okay, so by multiplying this one we will get a square that is equal to minus 2 5 minus 4 minus 3 2 minus 2 6 4 minus 1, and 3a is equal to 3 6 minus 3 0 3 minus 3 and 0 minus 3 3, right? So now we have all the required values to find a inverse. So now by substituting the values of a square and 3a in equation number 1, we will get here a inverse is equal to 1 by 3 into, we need to simplify this expression, then we will get minus 1 by 3 into 0 minus 1 3 4 1 minus 3 7 1, right? This is the value of a inverse. Here we need to find adjoint of a, right? So but here I have not find a inverse by the method of adjoint of a upon determinant of a. So I have directly the value of a inverse, that is minus 1 by 3 into 0 minus 1 minus 3 4 1 minus 3 7 1, right? And we all know that a inverse is equal to adjoint of a upon determinant of a, right? So the adjoint of a, that is equal to a inverse into determinant of a, right? So we have a inverse. If we find the determinant of a, then by multiplying it by a inverse we can find the value of adjoint of a, right? So here first of all we will find the determinant of a. Now we have also discussed that how to find the determinant. Then the determinant of 1 2 minus 1 0 1 minus 1 3 minus 1 1, that will be equal to minus 3, right? That is for the homework for the students again, that how to find the determinant, right? So this determinant is equal to minus 3. So the adjoint of a is equal to a inverse into determinant of a. So determinant, that is equal to minus 3 into a inverse, that is minus 1 by 3 0 minus 1 minus 1 minus 3 4 1 minus 3 7 1, and by simplifying, that is minus 3 into minus 1 by 3, that is equal to 1. So adjoint of a, that is equal to 0 minus 1 minus 3 4 1 minus 3 7 1. Okay, that is the value of adjoint of a. So this is the application of Cayley-Hamilton theorem. Using Cayley-Hamilton theorem we can find the adjoint of the given matrix as well using the a inverse. Usually if we use the formula adjoint of a upon determinant of a to find a inverse, first of all we need to find the determinant, then the adjoint, then we can find the inverse. Here using the inverse we can find the adjoint if we use the Cayley-Hamilton theorem. Okay, so this is about the Cayley-Hamilton theorem. So this is very important theorem from the exam point of view. So now let us look at the diagonalization of a matrix. So this is about how to find the diagonal matrix for any matrix A. Okay, so here diagonalization of a matrix A is a process of reduction of A to be a diagonal form. So first of all we need to clear that what is the diagonal form. That is, if we know the definition of diagonal matrix, then we can easily know what is the diagonal form. We know that the diagonal matrix is all the diagonal elements, if all the rest of diagonal elements will be 0 and we have only the values in the diagonal entries, right? That is the diagonal form. So to form the diagonal matrix from the given matrix A, we need, if A is related to D, by a similarity transformation such that D is equal to M inverse A into M, then A is reduced to the diagonal matrix D through the model matrix M. D is also called the spectral matrix of A, which is in the diagonal form. So if we want to find the diagonal matrix D, then we need to find the M inverse into A into M, right? So now reduction of any matrix to diagonal form. So if a square matrix A is of order n, has n linearly independent eigenvectors, we know how to find the eigenvectors, right? So if a square matrix A of order n has n linearly independent eigenvectors, then a matrix B can be found such that B inverse into AB is a diagonal matrix, right? Then note that the matrix B, what is matrix B? The matrix B which diagonalizes matrix A is called the model matrix of A, and that is obtained by grouping the eigenvectors of A into square matrix. If we have the eigenvectors of A, that we all know how to find the eigenvectors for any matrix. If we have the n linearly independent eigenvectors for any matrix A, if we arrange in the column wise all that vectors, then we can find the model matrix B, right? And by B inverse into A into B, we will get the diagonal matrix for any given matrix A. So as we have discussed in the note, that the matrix B which is diagonalizes A is called the model matrix of A, and that is obtained by grouping the eigenvectors of A into square matrix, right? So now what is the idea of similarity matrices? A square matrix B of order n is said to be similar to square matrix A of order n if B is equal to M inverse into A into M for some non-singular matrix M, right? So if B is equal to M inverse into A into M for some singular matrix M,